Every second, billions of multimedia frames move through memory. Modern multimedia systems are basically giant real-time data pipelines. Frames are continuously captured, buffered, encoded, decoded, streamed, and displayed. Bad memory management breaks real-time systems. And if memory handling becomes inefficient, entire pipeline suffers. So, in this video, let's understand memory management from the perspective of real multimedia systems. Okay, so before we jump into the exact memory layout, how it is defined in C, like stack, heap, memory, other memory regions, let's try to first understand why memory management becomes such a big deal in multimedia systems, right? Because honestly, multimedia engineering is basically this art of moving massive amounts of data efficiently in real time, right? You would agree with this. If you look at this diagram here, every stage in multimedia pipeline is continuously reading, writing, buffering, copying, processing, encoding, decoding, and finally displaying or saving a data as a file or in a display system. And that data is very huge. You just see this, a single 1080p RGB frame. What does this RGB mean is real red, green, blue color, different 3 channels whatever we capture in a color scheme or color data what we capture. So typically 1080p is full HD. So to full HD resolution is something like this, width into height. So 1920 by 1080 by into 3. So that means multiplying this would come around 6 MB per frame. So single frame capture will have around 6 MB of data, right? So how many frames you have in a single kind of 1 minute movie or 1 minute video? So if you say, like, suppose 1 minute is 60 seconds, right? So 60 seconds, so if you have 60 fps kind of 60 fps frame rate for a video, so you have 60 frames per second, right? So 1 minute is having 60 seconds, so 60 fps means 60 into 60, right? 60 into 60 into 6 MB, right? So this much data, if we calculate, let me switch to this, right? If we calculate multiplying this, so it is around 3600 into 6, that means 636 118 plus 210 00 MB. Roughly around 1 minute of video will have around 2.16 GB, 2.16 GB of data. So you can just imagine, right? Coming to the infographics, why the memory management matters in multimedia. So as I explained earlier, multimedia processes a huge amount of data all the time, right? So there are multiple systems being part of the multimedia pipeline. You can see there are video frames, there are audio buffers, there are camera sources, there are decoder and the AI tensors being parallelly utilized. There are different kind of multimedia data that has to be processed at a single time. I explained earlier, this is the data rate at 30 fps. If we are processing any multimedia data at 30 fps, we have to process around 180 megabytes of data per second. So just imagine if it is a 30 minutes video or even a 1 minute video, it would be a huge amount of data, right? So why memory layout impacts and how does memory impact some multimedia systems? There are different areas of impacts. How, if the memory is not being handled properly, what does it affects and what these kind of areas affects, right? So performance, if we talk about, there are, if we don't have a proper memory usage, will not have a proper GPU or you know CPU utilization, right? That has to be taken care of. If we don't allocate a proper buffer, there can be buffer underflows, buffer overflows, or there can be glitches, or there can be lag in the video, frame drops, right? So that has to be properly handled. Latency, what happens is, if there is no efficient memory access, there will be a latency in the real time pipelines. Suppose there is a CCTV camera being monitored somewhere. If there is no proper memory access or memory allocation given to the multimedia pipelines, then there is no use of this real time pipelines, right? So we need a proper efficient memory access for better latency. There will be frame drops if there is no proper memory management. There will be frame drops. There will be no buffers for the frames to properly fill in, and then the frames will be lost, and frames lost means there is loss of data. Cache efficiency, memory locality and alignment improve the cache hits and overall efficiency. So that is all CPU cache we are talking about. Stability means correct memory management prevents crashes, leaks, and data corruption. So overall pipeline, you can say there will be a stable pipeline. So how memory is handled in multimedia systems? So there are different methods. That is a very higher topic to discuss now, but this is just like an introduction or pre-introduction, you can say, so that you will understand why memory management in multimedia systems are very important. So pre-allocation buffer pools means buffers are pre-allocated and reused to avoid frequent alloc and malloc and fragmentation. So we have buffers which are which handles the data being saved, right? So that has to be pre-allocated, and so that it doesn't frequent freeing and allocation and deallocation will lead the memory areas to be fragmented, right? So suppose there is this area of memory, and let's say we allocate something here, and then again we freed out here, right? So this becomes empty, and again we allocate something here and then freed out here, right? This becomes empty, and any new data has to be it has to search where the free area is there randomly. So this has to avoid. Reuse and recycle, so buffers are recycled through the pools and queues. So there are different ways of handling the multimedia systems, ways of handling memory in multimedia systems. Okay, right? So continuous memory, DMA buffers, this is a very important topic that we will be dealing it later, but right now just to think of it, this is kind of very next level information that any new multimedia systems, that is very modern multimedia systems, use this. Zero copy pipelines, where data moves between the components without being copied. As you know, copying from one location to another involves huge usage of CPU, right? To avoid that, we have to use zero copy pipelines, where we just allocate certain kind of buffer, and the source writes here, and the sync the consumer reads the data from there. So the producer will write data and the consumer will read data. So this source will be shared among both the producer and the consumer, right? So this is how zero copy pipeline works. And shared memory, right? And hardware acceleration. Hardware acceleration is next level kind of handling system, where the modern multimedia pipelines use hardware acceleration everywhere, right? So we have NVIDIA, right? We have NVIDIA systems that use hardware accelerators, right? Intel machines also, right? Intel machines use hardware acceleration. We have encoders, decoders, many things are there actually. So if I talk about key the memory flow in the multimedia pipeline, you can see there are different components. This is all little advanced topic as of now to discuss, but you can see this camera source, capture buffers, processing buffers, encoder buffers, socket, decoder, display. These form a basic pipeline, multimedia pipeline, how data flows. So everywhere data has to be efficiently handled, efficiently encoded, efficiently decoded, efficiently transferred. Then only the whole pipeline will be kind of in a state where real time processing or any data loss can be avoided. These all things can be handled actually. So if I talk about key takeaway, memory is the lifeblood, right? So in multimedia there is nothing as important as handling memory. Everywhere, whatever you allocate, whatever you deallocate, right, memory has to be perfectly synchronized and perfectly handled, so that there is no loss of data, there is no loss of real time scenarios, and it is completely reliable. So understanding managing memory correctly allows you to build systems that are faster, more efficient, and more reliable, right? This is the basic crux of this infographic. Yeah, so this is the classic process memory layout in C. At the bottom, we have the text segment. This contains the compiled instructions of the program itself, whatever code we write in the C. These are the instructions code written. Then we have the initialized global variables that is stored in the dot data section of the memory. Then we have the BSS. We'll explore more. I'll tell you the basic, more details about each of the section, and I'll just write it here also. Just for now, we're going through the basic definition. So BSS has the uninitialized global variables. Heap is kind of used for dynamic memory allocation, and stack is where the function calls and the local variables live. So honestly, this looks like kind of academic, but for our use case in multimedia systems, how these regions become important, and where and all we store the multimedia buffers, multimedia data. We'll explore it in the further coming steps. So with going further, let's describe each of the section little bit in more detail. Right. So let's start with the code segment. Okay. So where this is where the machine instructions are saved, right? This is where executable code is being saved, all the functions, statements, and instructions that we write in the C code. Since that is we can't change the code, so it should be read only. So read only means it will go into the flash memory, that is also called ROM, that is non-volatile, so it should save in the ROM. And since this is read only, so we have the constants, whatever we declare with the variables in the functions as constants, that also goes into the dot text segment. So next comes the dot data. So dot data will be having all the globals, static variables declared, and this is all initialized. So all the initialized global static variables declared, that will come here, other than 0. So user is initializing the variables here other than 0, and these variables has to retain the values throughout the program because the user has explicitly initialized the values of the variables here. So this also will be stored in the flash because it has to retain the value that will come into the ROM, right? So whenever a variable is initialized, memory space is allocated in the data segment of the program's memory. That is, in short, you can say, right? Sorry for my bad handwriting. It would be a little difficult to read. I'll try to maintain it as good as possible. And then comes the BSS. So it is just the uninitialized globals and statics. So all the uninitialized globals and static variables in the code, and since it is uninitialized, so what happens is the OS, right? OS initializes to 0 when the program is being executed. Whenever the program is loaded on the memory, the OS initializes the BSS segment to explicitly to 0. So that is how the the variables are initialized here. The name BSS comes from some history naming. Actually, people have named it on something related to some section where the code starts. So usually it is called block started by symbol because the section starts with a symbol that defines the start of the block, right? So that is how the naming is done here, right? So next comes the we'll go to the stack segment first. Stack segment is responsible for all the function calls, right? All the function calls, and inside the function we have local variables, right? We have arguments passed on the function arguments. So these all come into the stack memory, right? And since this stack grows towards the lower address, so whatever comes at the last will be popped out at the first. So basically, whenever a function is being function calls are being called in a repetitive manner. So suppose function 1 is being called, it goes at this address, and then function 2 is being called, it goes at this address, and function 3 is being called, it goes at this address. So it goes like in a order of downwards. So if we need function 1 to be used, so we need to pop function 3 first and function 2 first, and then comes the function 1, we can pop it out. That is how the stack works. It goes down and all the function calls, local arguments and everything sits here, and this is a temporary memory, so it is kind of RAM, handled by RAM because it is volatile. So whenever a function is returned, so all the local and arguments, whatever was there, it will be lost from the memory, so it is being saved into the RAM memory. Yeah, so also if you add, right, so I can say these two contribute to something called static part of the memory, and these two, stack and heap, are something called dynamic part of the memory, since it can change the size and all, right? This is all fixed while the program is initialized or executed while the program is running, right? So this is all fixed kind of memory. It is all one time initialized and all thing is done. But these two memory spaces, they keep on dynamically changing depending on the variables initialized or uninitialized or returned when the function is being returned. So let's come towards the heap. It's like dynamic memory location, right? So it is usually happens when you runtime, when you have to allocate the memory at the runtime. It is all being handled through programmers. So this is programmers have some APIs called malloc and callocs, These are all called by programmers, and this has to be freed upon when the program is ended or when the memory section is not being used. So that is all being handled by the programmer, right? So this provides a flexibility in allocating and deallocating, right? So this is all kind of heap. It comes into the heap section. So what happens, what we have understood in this memory layout of a C program is, so we need to properly and efficiently manage the memory. For example, in multimedia systems, right, we have lot of memory spaces to be handled, right? So we need an efficient way of handling these memory locations, because we need to avoid issues like memory leaks, buffer overflows, right? So organizing data in the memory itself is a very challenging part, and programmers have to implement certain ways of handling the memory so that data is being properly handled and properly used whenever it is required to be used. Okay, so let's jump into the code section and let's try to understand the variables, how in the code when the variable is declared and how it is declared and where the memory allocation happens, right? So we'll write a short C code and then we'll try to understand each variable declared and where it is being saved. So let's quickly make some working directory. So I'll do mkdir memory layout and do ls. We'll go into the memory layout folder, clear out things, right? Nothing is there. So let's make a file called memory layout .c, and the file is being created. Let's open that by going into the folder. Okay, let's close this. So okay, so let's never mind, this is all coming from the Copilot auto completion, so just ignore this as of now. So what we'll do is we'll declare some variables and we'll try to understand where all those variables sit and how the code looks. So we'll do something called include some directories. By the way, it's all the VS Code is running on a virtual machine, that is Ubuntu 22.04 that I have in WSL. So it's all about Linux environment right now, what you can see here. Okay, so let's declare some globals. We'll write it global initialized. We'll have global uninitialized. Okay, so as you know, these are all global variables. This is how the global variables are declared in C language. Let's define a function which doesn't take any arguments right now. Let's define a simple function. All the local variable. I'm just writing the variable name as per the memory allocation space. So you can see here, this is a stack variable, this is a global uninitialized, this is a global initialized, right? So that it becomes clear how the memory allocation happens for each variable what you see in the code. So heap allocation happens like this. And inside, after declaring these variables, let's print those variables addresses. We'll try to understand how the address behaves and where does the address sit on, because the different memory locations will have different address space, right? So we'll try to print those statements. So what I'll do is I'll just copy paste few lines of code that I've already written, so that it will be easier and faster. Okay, so we have this print statements. Let's I'll just try to rename those variable names. Okay, so this is all done, and then let's go and free the heap memory. As you know, we need to free, programmer has to free the heap allocated memory, because it is dynamically allocated, so we need to free that also, right? So this is done in the function call, and then let's write the main function. We'll call the demo function here and then return from the main simply, right? So we have this C code ready. Let's see what happens when we compile it. So there is this is the compilation code. We do compile the C language using this GCC compiler, and we have to write this .c file, and the output dot, usually the output file will be .out if we don't don't name it something like this, and once you name it the object file something particularly, so it will be saved as memory layout file like that. So let it compile, and if you do ls, you can see the this is the source code file, compiled source file, and then let's run that source code. Right, so these are all the addresses, what you can see here. Text segment starts from this address, right? Initialized data segment starts from something this address, right? BSS statement starts from something this, stack variable starts from something this, and the heap variable starts from something this. You can see somewhat similar scenarios when you have you must have watched the memory layout image, right? So let me bring it here, and just go through that. So you can see text, data, BSS, heap, these all four comes together, and stack somewhere lies above, right? So you can see the relation here in the code as well. So what you can see here is the starting address, right? You can starting numbers of the address 5E0876 up till I would say 87, right? These addresses are same for text, data, BSS, and heap. So that means all those four memory sections lie close to each other, and all different last digits will be different, of course, because of the size, right? In hexadecimal we represent those sizes different, right? So these values will be of course differently written here, right? So you can see the relation of those memory locations like that. And of course stack variable will be located somewhere above, very at the higher addresses. So you can see the higher address being referred to like this. Okay, so now the reason multimedia engineers care about this is because video systems process massive amounts of data continuously. A single video frame itself can become huge, as you can see, as you might have seen that, right? So let's test it once, and then let's see how in the real world, if we declare any kind of stack memory as how we do usually and use it for our multimedia systems, what happens. Okay, so here is a simple code that I will be compiling and running. As you can see, we have a frame kind of a buffer, what we have originally for multimedia systems buffer, right? So it is kind of size of 1920 cross 1080 cross 3. So we have this 3 RGB colors, and this is the frame width and height, right? So if we compile it and let's test it whether it runs or not. So I'll just run this test.c using this GC compilation, and yeah, so it compiled, and then now let's run the application. Whoa, so it said frame allocated. Wow. So I think what we remember from the previous discussion, right? You might see if we multiply this, right? It is coming around 6 MB for one frame, right? This is around 6 MB for a single frame. But now I will do one thing. Let's multiply it for at least 2 frames. Okay? And then check how it is. Wow, segmentation fault. So as you can just see, if we just add 2 frames for this much data, the stack memory is getting full and we can't allocate any further space. Also there is a command which is called ulimit, right? This tells us the stack size. So for in my system, the size is around 8192 bytes. So it comes around 8 MB. So as you can see, this is 6 MB and multiplied by 12 MB. If you put 12 MB stack size, segmentation fault comes because the stack size is in my system is around 8 MB. So yeah, lastly you saw, right, why multimedia systems usually don't place huge frame buffers on the stack. So since stack space is limited, so you have to place large video buffers, what we use in multimedia systems, on heap instead of stack, so that stack overflows or system or memory crash doesn't happen. Okay, so let's go into the heap example. Here you can see there is a allocation being made in the heap using malloc function. It is the same frame, a single frame of 3 RGB colors of 1080p being allocated in the malloc, using malloc in the heap section. This is the buffer allocation, and these are some error checks, and finally if everything happens correctly, we will be printing the message called the frame buffer is allocated on the heap, and then we will be finally freeing the memory, right? So let's test this example. gcc heap.test no heap.test, right? Compile it and then run it. So yeah, it says frame buffer allocation on heap is successful, and even if we increase the size by getting 2 frames, then and compiling it and running it, still the heap allocation is happening on the system because it's dynamic, and hopefully the heap doesn't get run out. Yeah, so as you saw, right, we can allocate as many amount of memory on the heap, but there is a limitation. That limitation we will talk later how we can check it, right? So real multimedia frameworks, like there are certain frameworks which is kind of multimedia based frameworks like GStreamer, FFmpeg, camera pipelines, any hardware codecs. These are all dependent on heavily on dynamic memory allocation internally, right? So everything, whatever happens in those frameworks, those are handled internally using heap allocation. Because video pipelines continuously allocate, recycle, and move buffers between different components, so it is easier to use dynamic allocation. Okay, so this is the kind of engineering content I want to explore on this channel. We'll deal with internals, how it is related to multimedia systems, Linux command systems, Linux architecture, how it is designed for multimedia systems, how multimedia systems use that architecture for their internal construction of pipelines. And yeah, so if you are into this understanding, and eager to learn on how modern multimedia systems actually work under the hood, just subscribe, because there's a lot more coming on your way, and hopefully we'll see you on the next one.